Hello, my name is Aria Smith, and this is my presentation for Physics 1 Lab 2 Projectile Motion. The purpose of this lab was to compare projectile motion data between the observed data on a video and predicted data using GlowScript, which one considered gravity and the other one considered gravity and drag. The observed data, as I kind of said, was found by uploading a video to Tracker, which is a software to track the position of each position of the ball in motion, and the predicted values were used GlowScript. Some key concepts: we use Newton's second law, position update formula, and velocity update formula as seen below, as well as Earth's gravity, which is negative mass times gravity in the y direction, and the drag force. The experiment, the system was a paper ball which had a mass of 3.42 grams, surroundings which included air resistance, the initial toss of the ball, and force of gravity. Initial conditions / assumptions: F net is the force of gravity and drag only, the initial throw of the ball, and moving in the positive x direction. A good note to make, if you can kind of see the graph, we'll get into that in a second, but the ball was not tossed at the origin, it was tossed in a positive y direction, starting place. This is the code that went into GlowScript for the initial conditions. As we can see, the mass of the ball, the initial position and the initial velocity, and time, the starting time, and delta t, as well as force of gravity and drag that we calculated to be 0.001. Calculations. The most notable part of this is where it says to calculate the net force. We added equations: speed equals magnitude times ball velocity, the drag equation, force of gravity being the ball's mass times gravity in the negative y direction, and F net being force of gravity plus drag force. This figure compares and contrasts between the observed and predicted values. As we can see, all three of the values are in this figure. We have the observed tracker data, the GlowScript with data with gravity, and the GlowScript data with gravity and drag. Some similarities: they all seem to take pretty much the same shape, mostly going in the positive x, negative y direction, starting not at the origin, as I kind of mentioned previously. Some differences: the observed model travels further in the positive x direction and does not go as deep in the negative y direction as early as the GlowScript data does. And I believe that this kind of shows that the predicted model overshot the effects of air resistance, as the observed tracker data is what really happened. Potential sources of error to note: the ball was not thrown in a parabola shape, but more of a thrown and watch it fall down to the table kind of shape, the kind of like the second half of a parabola, which this decreased the amount of data that we were able to generate from Tracker. Tracker is also an older software. My computer's on the older end, so that can create glitches, which could also account for less data points generated. There's also could always be calculation errors, whether that's human error or computationally. One of the discussion questions asked if any of the models predicted a terminal velocity. So the computational model, considering both gravity and drag, had a downward slope and eventually levels out, which shows for a terminal velocity. And as we can see on the photo on the right, this graph was generated by GlowScript for that second, for the code with gravity and drag considered. Also asked to imagine if the object was initially thrown straight up in the air with the same initial speed as the first experiment, if this object would take the same amount of time, longer or shorter, to reach the ground as it did in the original experiment. I said that the object would take longer to reach the surface, the table surface, as if it was thrown in a projectile motion fashion. If the object was thrown upward, even at the same speed, it would eventually slow down, hit a peak, and then start to move downwards with an increased speed. However, because of the slowdown and speed up property, throwing an object straight up in the air with the same initial speed would take more time than our original experiment. Additionally, to support this, I used some calculations using Newton's second law, as you can see below, and the delta t turned out to be 0.53 seconds, which is greater than the change in time for our initial experiment. Thank you.